Hello, welcome to this lesson in the Linear Algebra Tutor. Up until this point, we've reviewed a lot of material that you probably have been exposed to in other classes at one form or another, but we're kind of recasting it in this realm of linear algebra. For instance, we talked about vectors a minute ago in the last section, and we talked about how they're really just the same concept as these guys called n-tuples, which are just listings of numbers. And the fact that we know how to take the dot product of two vectors really just translates to the regular old matrix multiplication rule that we already know from matrix multiplication. So start to get used to the idea of a vector basically being a matrix, a type of matrix, because in a moment we're going to be dealing a lot more with vectors in this class, and that's the connection, that basically vectors are simply matrices. If you're three-dimensional space, you'd have three components in that column matrix there. Now, as you've probably guessed up till now, a lot of linear algebra is basically dealing with definitions and making those connections clearly like we've been doing in the last section. So in this lesson, what we're going to do is just go over a few more special types of matrices. Very, very simple, but I want to make them bulletproof and very easy for you to understand. The first one is called an identity matrix. We're going to be dealing with identity matrices all throughout this class in your problems and also in proofs and things like that. So let's go and talk about the concept of an identity matrix. Very, very simple. The identity matrix, the way you usually see it represented in a linear algebra book is the capital I with a subscript n. You'll understand what the n means in just a second. If I have an identity matrix, I sub 2, see, notice in this case n is equal to 2, then it looks like this. Basically, it means a 2 by 2 matrix with the number 1 along the diagonal elements and zeros everywhere else. All right, so the identity matrix is a general term. You can have an identity matrix for 2 by 2, for 3 by 3, for 4 by 4, for 5 by 5. So that's why we have the number, the letter n there, telling you that you can generate an identity matrix of any size, but it's always going to be a square matrix. So here's the identity matrix I sub 2. In the way that you construct it is you have 1s on the diagonal, zeros everywhere else. Now we can also have, for instance, an identity matrix I sub 3. What do you think that would look like? Well, it's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. Notice in this case we have 1s along the diagonal, zeros everywhere else on the off-diagonal elements. And you can kind of continue on. You can make I sub 4 and I sub 5. In each of those cases, you'll have 1s along the diagonal elements and zeros everywhere else. That's what an identity matrix is. So if you ever see I sub n running around a proof or a theorem in your linear algebra book, just replace it with this concept of an identity matrix with 1s on the diagonal. Now, why do we care about that? Because an identity matrix is special because of the following reason. It's pretty simple. You know, once we go over it, it'll be pretty easy for you. If you take a matrix A, any matrix, and you multiply it by the identity matrix of the proper size, the same size as A, then what you're going to get is you're going to get the same matrix back. Now, obviously, the sizes of the matrices that you choose to do the here for A and I, they have to be able to generate a multiplication. You know, matrix multiplication, we said, is not always defined. So you need to make sure your identity matrix is of the proper size so that you can actually do the multiplication. But to give you an example of how you would do this, I could generate a matrix as follows: 1, 3, 4, 2, 0, 1, 1, 1, 1, right? And that could be matrix A, right? And I can multiply it by matrix I. Now, I can't just choose any old matrix. I can't choose a 2 by 2 to multiply here, because if I put a 2 by 2 matrix, then the multiplication isn't going to be of the right dimensionality. So I need to choose a 3 by 3 matrix, 0, 1, 0, 0, 0, 1. This is going to work because, and I'll just go ahead and put I sub 3 here. This is going to work because we can go over and down. So the number of columns this direction equals the number of rows this direction. So this multiplication is valid. Now, if we actually do this, let's go and do this multiplication real quick and kind of show you. If we go over and down, notice we have 1 times 1, give you 1, 3 times 0, 4 times 0. So the zeros kind of kill everything else. 1 times 1 remains. All right? And let's just go over to the right. So we'll go over and down this way. So we have 1 times 0 giving you nothing, 3 times 1 giving you 3, 4 times 0 giving you nothing. So the 3 survives. And if we go over and down this way, this gives you 0, this gives you 0, this gives you 4. So you can see what's happening is already the original matrix here is being mirrored in the answer. The identity matrix is going to make it so that if you carry out this multiplication, what you're going to get is the exact elements that you started with. So the initial matrix A, when you multiply by an identity matrix, is equal to itself. All right, and if you want to just spot check that, you can go over and down this way. 1 times 1 giving you 1, 0 giving you 0 here, this giving you 0 here. So if you go over and down this way, you're going to get the number 1. That's that guy down there. So I encourage you to do the full multiplication with all the rows and all the columns, and you'll see that anytime you multiply by an identity matrix, presuming that the dimensions of A and I are such that you can multiply them, you're going to get the same matrix that you started with. All right, and that's the beauty of that. How you're going to use this, can't really express it too much right now because the application of when you actually need to use it will come a little bit later, but I want you to understand these definitions, make them clear for you. All right, the next thing we're going to talk about is called triangular matrices. Now I want to make sure you understand when you read in a textbook or see in a lecture somebody talks about a triangle matrix, I want you to understand what that is. So let me give you a couple quick examples. 1, 0, 0, 2, 1, 0, 3, 4, 2. All right? This is called lower triangular matrix. And the reason is because the non-zero elements form a lower triangle here. So in other words, if you had the matrix here and you have the matrix here, it forms a triangle like this. When the diagonal elements here are part of this line here, and the other non-zero elements are inscribed in sort of a triangle. Now this is a 3 by 3 matrix, but it also goes for larger matrices, from 5 by 5 and so on. A lower triangular matrix would have to basically be diagonal elements and then on down to the bottom, where everything above the diagonal like this up and to the right would be all zeros. That's going to be called a lower triangular matrix. So you might also guess then that I can draw an upper triangular matrix. 1, 2, 3, 0, 4, 2, 0, 0, 9. This is an upper triangular, I'll use the word triangular represented by a triangle matrix. And in general, if you have a matrix like this, an upper triangular matrix will look like something like this, where this line here is the diagonal elements, they're non-zero. We form an upper triangle here, these zeros here, everything on the other side of the diagonal is 0. All right? And then finally, you can also have something just called a diagonal matrix. Very, very simple concept to understand. I'm, again, representing these with 3 by 3 matrices, but it extends to higher dimensionality as well. 0, 2, 0, 0, 0, negative 3. This is called a diagonal matrix. In a diagonal matrix, basically the only non-zero elements are going to be strictly along the diagonal, like what we have right here. So here we have non-zero elements on the diagonal, but everything to the upper right and everything to the lower left are all zeros. How are these useful? Usually you'll see things like this in proofs. You know, there are ways to take a matrix and split it into a triangular upper matrix and a lower triangular matrix, and then manipulate them separately. So I just want you to understand the terminology as we get into matrix algebra. When you see something like triangle matrix, you're not freaked out. It just means basically what we've talked about right here. Now the next thing I want to mention to you is something that you'll definitely see before. We talked about, remember we talked about the transpose of a matrix. Transpose is when you take the rows of the original matrix and turn them into columns, or equivalently take columns and turn them into rows. Basically you're flipping the rows and the columns around. That's what we call the transpose. We already covered that. So related to that, we have something called a symmetric matrix. So if somebody on the test says, hey, tell me if this matrix is symmetric or not, you need to know what to look for. And the test to see if a matrix is symmetric is if the matrix is equal to its transpose. If it's equal to its transpose, it's said to be symmetric. All right, because remember, when you have a matrix, you're flipping the rows and flipping the columns. So it's very likely in general that since you're flipping the matrix around like that, what you get for the transpose will be totally different than what you start with. But in a very special case, if you construct the matrix properly and you take the transpose, you'll actually get the same matrix that you started with. That's called symmetric matrix. So let's go ahead and talk about that and give you a quick example of that. let's say that we have the matrix A, 1, 7, 3, 7, 4, negative 5, 3, negative 5, and 6. All right, so how do you figure out if it's symmetric? Well, the first thing you need to do is construct the matrix transpose. And let's see if these two are equal. So the way I do it is I turn the rows into columns. So I go across 1, 7, 3 and turn that into a column. And then I go here, 7, 4, negative 5, and turn that into a column. And then I go here, 3, negative 5, and 6, and I turn that into a column. This is the transpose of the original matrix, but notice 1, 7, 3, 1, 7, 3, 7, 4, negative 5, 7, 4, negative 5, 3, negative 5, 6, 3, negative 5, 6. The transpose of the matrix is the same as the original matrix. Now, that's why we call it symmetric. All right, now, in general, that's not going to be the case. In general, that's not going to be the case, because if you have a weirdly shaped matrix, taking columns over here, flipping them in the rows, then in general you're going to get something different. But this particular matrix is special, and you can kind of see that because if you notice, if you were to put like a sheet of paper right here along the diagonal, you notice you have a mirror image. The 7 is mirrored on both sides of the diagonal. The 3 is mirrored on both sides of the diagonal. The negative 5 is mirrored on both sides of the diagonal. And the diagonal elements themselves, 1, 4, and 6, are actually just remaining in the same place. So if you kind of take this matrix and fold it in half like a sandwich or something, you're going to end up with a mirror image across the diagonal elements. That's why we call it symmetric, because symmetry means you have some duplicity somewhere, some kind of reflection, so to speak. So that's what we call symmetric matrix. But the test of it is you form the transpose, see if you get the same thing, and then you're done. Now the last thing, that was called a symmetric matrix. There's actually something called skew symmetric matrix. Right, skew symmetric. And that's very, very similarly related. And that is, if you have a matrix A and you take its transpose, then what you get is that the original matrix A is equal to negative of its transpose. So again, it's very similar to before. It's just that the elements are a mirror image, but they're negated relative to the original matrix. So let's give a quick example and show you how to figure out if a matrix is skew symmetric or not. So what we have is matrix A, 0, 2, negative 1, negative 2, 0, negative 4, 1, 4, 0. All right. Now the next step, once we get our matrix, is let's go ahead and form its transpose. Do things one step at a time. Let's go ahead and form its transpose first. So I'll take this row and make it into a column. 0, 2, negative 1. I'll take this row and make it a column. So it'll be negative 2, 0, negative 4. And then I'll take this and make it a column, 1, 4, 0. All right, so this is the matrix transpose. And then as a final step, I'm going to take the negative of its transpose. So the negative of that matrix that we just created, notice we're multiplying the matrix by negative 1, so all we're doing is going to change all the signs of the elements. So it'd be 0, 2, 1, negative 2, 0, negative 4, 1, 4, and 0. And that is the negative of the transpose. Now notice what we have, 0, 2, negative 1, 0, 2, and I forgot a negative 1 here. We'll stick that in right there. Notice that we have a 1 right here, and here's a negative 1, so I just forgot 1 there. So what we have is 0, 2, negative 1, negative 2, 0, negative 4, 1, 4, 0. These all match what the original matrix was. So the original matrix is equal to the negative of its transpose. Basically is what we have going on there. All right, and that's how you arrive if something is skew symmetric. So it's pretty much symmetric. I mean, the absolute value of the transpose looking at the original matrix, the same numbers are everywhere. It's just that you have to put a negative sign in front to make them actually equal. That's called skew symmetric. So occasionally on an exam or a quiz or in a homework problem, you'll be given a matrix and have to determine if it's symmetric or skew symmetric or find its transpose, things like that. So I just want to give you a couple quick examples to solidify that process. That's what we've been doing basically here. So we've just taken a few minutes to talk about some special matrices, identity matrix, and so on, mainly trying to tidy up the definitions, the things that you'll read in the book, and you'll need to know what the heck they're talking about in order to follow the lesson. What we're going to do in the next few sections is begin to turn our attention a little more heavily to vectors. And we've done that a little bit before. We've kind of made the connection between vectors and matrices, and I hope that by now you have a good warm fuzzy that a vector is really just a triplet of numbers if it's a three-dimensional vector. If it's a two-dimensional vector, it's just two numbers. But in any case, it can be represented as a matrix because a matrix is just a listing of numbers. That's all it is. And so we're going to learn how to manipulate those in terms of vectors using the rules of linear algebra. So we're going to start to deal with vectors here in the next lesson or two. And keep in mind that as we go way through the course, we're going to go through a lot of topics between here and there, but eventually we'll be talking a whole lot more in terms of vectors and manipulating vectors in different vector spaces. So definitely don't fall asleep when we're learning about the vector stuff, because the second half of linear algebra is all about vector spaces, how to rotate vectors, how to transform vectors, how to form new vector coordinate axes, and all of that stuff. So we're building up our skills in learning to treat vectors as matrices so that when we manipulate them, we'll be manipulating them in the context of linear algebra and all the transformations that are to come. So let's go on to the next section. We'll continue working with vectors in linear algebra.